Problem 2 from lesson 9 is a good example of the application of the combined gas equation and the importance of using the absolute temperature scale. So let's look at this problem. So here we have a sample of gas that's initially at 25 degrees Celsius and it's changing from 2.0 to 3.5 atmospheres at constant volume, and we're trying to find the final temperature. So to do this problem, we can use the combined gas equation, which is P1V1 over T1 is equal to P2V2 over T2. And what we're going to be solving for is T2. We want to know this final temperature. But we can first simplify this equation because we know that we're at constant volume. So that means that our V1 is equal to V2, so since they're the same on both sides of the equation, we can simply cancel them out. Okay, so now we need to go ahead and solve for T2. I think the easiest way to solve for T2 is to take the inverse of both sides, or basically you're just flipping over both sides of your equation. So now you have let me erase that. So now you have T1 over P1 is equal to T2 over P2. And again, we're solving for T2, so now we just need to multiply P2 on both sides. Our P2's cancel out on the right-hand side, so we're left with T2 is equal to P2 times T1 over P1. But it's really important that when we're plugging in our temperature, that we put in our temperature as Kelvin rather than Celsius. And that's because Kelvin is an absolute temperature scale. What that means is that 200 Kelvin is twice as hot as 100 Kelvin. But that isn't exactly true on the Celsius scale. So we need to always use our temperature in Kelvin. So always use Kelvin for our ideal gas laws. And if you don't use Kelvin, then this proportionality doesn't work out the way it should. So that means we need to convert 25 degrees Celsius into Kelvin. And remember that absolute zero is negative 273 Celsius. So 0 degrees Celsius, we'll just write this out, is equal to 273 Kelvin. So we just need to add 273 Kelvin to 25 degrees Celsius to get it into we need to add 273 to 25 to convert Celsius into Kelvin. So our T1 is going to be 25 plus 273, which is 298 Kelvin. Okay, so we can go ahead and plug this into our equation. So we can say that T2 is equal to 3.5 atmospheres times 298 Kelvin over 2.0 ATM. Our atmospheres cancel out, and if you do this calculation, you'll get 522 Kelvin. But now the problem is asking for our temperature in Celsius. So that means we need to now subtract off 273 to get this back into Celsius. So to do that, we simply minus 273, and we get a final answer of 249 degrees Celsius. So that's your answer.